First of all, I would like to thank the organizers for allowing me to present my work. And here, what I'm going to show today is substantially what I did during my period with Lyndon at EPFL. And there, I tried to develop a method to hyperpolarize, or to, let's say, improve the sensitivity of solid state NMR spectroscopy through optical irradiation of the sample. So no microwaves, just light irradiation of the rotor. Um, so why do we care about sensitivity in NMR spectroscopy? Well, I mean, you are all familiar with NMR. We all know that NMR is a beautiful technique, but unfortunately is also a very insensitive one. And that is because NMR spectroscopy probes the population imbalance between the nuclear spin states, or better, the polarization of nuclear spin transitions. And that polarization under conventional let's say, situations is quite tiny, just a few ppm. And this low polarization is due to the fact that NMR transitions are very low in energy. So, for example, if we compare NMR transitions with electron spin transitions, so EPR transitions, we see that the latter are, roughly speaking, three orders of magnitude higher in energy than NMR transitions, and therefore these EPR transitions are three orders of magnitude more polarized than NMR transitions. And actually, this effect is exploited in solid-state NMR spectroscopy by DNP. So with the application of microwaves, we can transfer this thermal electron spin polarization to the nuclei to enhance the sensitivity of solid-state NMR spectroscopy. And DNP, as I guess all of you already know, is an extremely useful technique, especially in solid state, because it allows to increase the sensitivity of NMR by several orders of magnitude. So here what I'm showing you now is one of the earliest reports about the use of DNP at high magnetic fields. And for example, in this case, the authors of this paper were able to detect the blue spectrum, which is the carbon-13 NMR spectrum of some organic species grafted on the surface of mesoporous silica in just half an hour. And without the use of DNP, to get the same signal to noise as the blue spectrum, they estimated that they would have needed, roughly speaking, 70 days of acquisition, something that is totally unreasonable. Okay, so how does a DNP experiment work? Well, we are in the context of solid-state NMR spectroscopy. So our sample typically consists in a very finely ground powder. And so this circle here is one of the grains of this powder. And we take our powdered sample and we impregnate this sample with a solution containing some paramagnetic species, for example, this stable bis nitroxide, because these are, let's say, very efficient for cross-effect DNP in solids. So we impregnate our powder and then we flash freeze the sample so that this solution, this impregnating solution, forms a glassy matrix around the particle of our sample. And then we apply microwaves. So upon the application of microwaves, we transfer the electron spin polarization from the paramagnetic species to nearby nuclei. And typically in this transfer, we target at proton spins because then by proton-proton spin diffusion, which is a spontaneous process, we can more or less uniformly polarize the entire glassy matrix around the sample. And then finally, either by spontaneous spin diffusion, if also our sample is protonated, for example, or by cross-polarization, we can relay this hyperpolarization from this glassy matrix to the bulk of our sample, ultimately enhancing its NMR signal. So the question that I wanted to answer during my postdoc with Lyndon was quite simple. And so if we can improve the sensitivity of NMR spectroscopy by utilizing the polarization of EPR transitions, can we actually do the same thing but using the polarization of optical transitions? And the reason is that optical transitions are even higher in energy than EPR transitions, and typically in optical transitions only the ground state is populated, meaning that they are 100% polarized. So if we can do that, we could in principle achieve up to 100% nuclear spin polarization. Of course, this is an extremely long goal, but ideally this would be possible. So what we were thinking was to then design a protocol quite similar to that of DNP, of microwave-induced DNP. So again, we have our sample, we flash freeze it. In this case, we use light instead of microwaves. But if we want to do that, we need an optically active polarizing agent that actually targets specifically at proton spins in solid, because we still need this proton-proton spin diffusion step to occur, because this is probably the most efficient way to relay the hyperpolarization over relatively long distances in the solid state. So this is really crucial for the design of our protocol. So the idea of optical hyperpolarization in NMR spectroscopy, both in liquids and in solids, is not a new concept. There are many techniques that can achieve some form of optical induced nuclear polarization. And one of them is actually photochemically induced DNP, or photo-kidnap for short. So photo-kidnap in the solid state is observed in donor acceptor systems, in covalently linked donor acceptor systems that undergo charge separation processes upon photo excitation, so upon illumination with visible light. And photo-kidnap in solids has been studied since the 1990s. Now one of the biggest names in photo-kidnap is, for example, Jörg Matisik. But yeah, so photo-kidnap has been studied since the 1990s, especially on biomolecular systems, so flavoproteins and photosynthetic reaction centers. But the problem with these systems is that typically only carbon-13 and nitrogen-15 photokidnap effects are observed. And this is a problem because carbon-13 and nitrogen-15 have a quite inefficient spin diffusion because of their low natural abundance and also low gyromagnetic ratio. And so if we create polarization on this nuclei, this polarization remains confined within the donor acceptor system. But if we want to use photo-kidnap as a way to generate bulk hyperpolarization, again, we need proton photo-kidnap to occur in the solid state. So how can we achieve proton photo-kidnap in solids? Well, what we did was to focus on these donor chromophore acceptor synthetic molecules rather than biosolids. And in particular, we initially focused on this one that was developed by the group of Michael Wasilewski. in the 1990s as well. And for example, I mean, we focus on this one because it is very, very well characterized in the literature. We know that if we shine blue light on the central chromophore of the molecule, we have a charge separation step. So basically, we create a transient radical pair, a cationic radical center on the donor side of the molecule and an anionic radical center on the acceptor side of the molecule. And the creation of this radical pair, or better, spin correlated radical pair, we will see why spin correlated in a few slides. It is one of the fundamental ingredients for photo-kidnap to occur in solids. Okay, so we took this molecule and then we prepared a frozen solution at 1 millimolar concentration of photopol in ortho-terphenyl, which is this glassy agent here. It is a widely used glassy matrix for both DNP and EPR experiments. So we prepared this frozen solution at 1 millimolar concentration, and we acquired the proton NMR signal of the sample at 0.3 Tesla, so no high magnetic fields yet, so it's just 13 megahertz proton Larmor frequency. And also we recorded the spectrum under static conditions. So this is a solid state spectrum, therefore the proton NMR signal is just a very broad potato in this case. And in the dark, when so when we acquire the spectrum in the dark, nothing really interesting happens. But the cool part is when we shine a continuous light on the sample while we are acquiring the signal. Because if we do that, we see that the bulk NMR signal of the sample gets inverted and also amplified by a factor of -16. And so what is happening here is that the photopole is creating locally hyperpolarization via proton photokidnap at this magnetic field, and then by spin diffusion, by proton-proton spin diffusion, this hyperpolarization is spontaneously relayed to the bulk of the OTP matrix. We also investigated the generation of, so the build-up of polarization with and without light. And we observed in this case that with light, the build-up time is roughly speaking a factor of 2 faster than that without light. And therefore also the signal enhancement factor is time dependent. So we get a maximum of -16, roughly speaking, at 20-second repolarization delay, which is the spectra that I just showed you in the slide before. But then the signal enhancement factor stabilizes around -9 for very long repolarization delays. And if you are not yet convinced that what I'm showing you is a bulk effect, we performed one other experiment with a different concentration of photopole in the frozen solution. And so we saw that at both 1 millimolar and 0.1 millimolar photopole concentration, so with both concentrations, we observed the same steady state signal enhancement factor, meaning that what we are seeing here is really the NMR signal of the OTP matrix, but also meaning that the matrix is uniformly polarized. So the signal is uniformly enhanced across the bulk. So in order to continue, I thought that might be useful to show or to give you an idea of how actually photokidnap works in the solid state. So this is the kind of photocycle that this donor acceptor system undergo. in the solid state. So if the molecule resides in the dark, it populates its electronic ground state here. But then when we photoexcite the molecule, indeed, I mean, we get to an excited state, which is quite unstable, and this state typically undergoes charge, intramolecular charge separation on the picosecond time scale, at least for photopole, creating a spin correlated radical pair. And why spin correlated? Well, because these two radical centers are coupled because they are in close proximity, and also they are this radical pair is created typically in the electronic singlet state, because we start from a singlet precursor, so because of spin conservation rules, because indeed our molecule is typically diamagnetic in the ground state. Then, because of the presence of hyperfine couplings, so couplings between the radical pair and the nuclei in the molecule, this radical pair can coherently evolve between its singlet state and at high magnetic field, the T0 state, so the triplet T0 state. Then this radical pair is also a transient species, so charges after a while, they want to recombine. If they recombine while occupying the singlet electron spin state, we achieve again the initial ground state. But if charges recombine while in the triplet electron spin state, we have the creation of a so-called neutral triplet state, where the triplet is localized either on the donor or the acceptor side of the molecule. And eventually, also this triplet state decays to the ground state, and this photocycle can repeat over and over many, many times. And in solids, photo-kidnap can develop according to three different mechanisms, which are termed differential relaxation, differential decay, and free spin mixing. So these three mechanisms are not mutually exclusive. They can be active all at once. And I mean, now I'm going to show you how they actually act in solids. But before doing that, especially for differential relaxation and differential decay, I need to introduce the concept of spin sorting. So imagine that you have your sample in the dark, and we have only one spin, one half in our molecule. So half of the molecules we have the spin in the alpha state. The other half we have the molecules. The other half of the molecules will have the spin in the beta state. And the molecule is placed, the ensemble of molecules is placed in a magnetic field. So the Hamiltonian for the moment is just the Zeeman Hamiltonian. So alpha and beta states are eigenstates of this Hamiltonian. Therefore, nothing happens to the nuclei. So when we photoexcite the molecule, again, nothing happens. We preserve the nuclear spin state. And that is also true during the intramolecular electron transfer process. But now things start to be different, because we have the creation of the spin-correlated radical pair. So at high magnetic field, now this is the relevant spin Hamiltonian. So we have the radical pair, and what we have in the Hamiltonian are basically the Zeeman term for the radical pair, where what matters is the electron spin Larmor frequency difference between the two radical centers. We have again the Zeeman term for the nucleus. Then we have this D term, which describes the electron coupling in the radical pair. And also we have the A and B terms, which are the secular and pseudo-secular component of the hyperfine coupling between the nuclear spin and the radical pair. So if we represent this Hamiltonian as a matrix, and we use the Zeeman basis for the nuclear spins and the singlet triplet basis for the radical pair, we get something like this. So let's ignore for the moment the effect of the pseudo-secular component of the hyperfine coupling. So you can see that the Hamiltonian is not diagonal in this basis representation, which means that the singlet radical pair state is not an eigenstate of the Hamiltonian, because we have these coherence terms, or these yellow and red coherence terms in this Hamiltonian. So what happens is that anyway, if we are in the situation where the electron spin Larmor frequency difference matches half of the hyperfine coupling, either the two yellow terms or the two red terms go to zero, suppressing the coherent evolution of the radical pair with the nuclear spin in one or the other state. And what does it do? Well, this effect simply sorts the nuclear spins between the singlet and triplet radical pair states. So we have not created yet any net nuclear spin polarization. We simply have distributed the alpha and beta spins of the nuclei between the singlet and triplet states of the radical pair. So now, how can we actually develop nuclear spin hyperpolarization via a photo-CIDNP? So let's first talk about differential relaxation. So we start from this spin sorted configuration. Then, the radical pair is a transient species, as I mentioned you before. So the charges want to recombine. And if they recombine in the single state, we go back to the ground state. If they recombine in the triplet state, we go to this so-called neutral triplet state. But now there is no radical pair anymore, so the Hamiltonian now only comprises the Zeeman term for the nuclear spin. So now the nuclear spin is locked in this configuration for these two states of the photocycle. But what happens, however, is that this neutral triplet state is a paramagnetic species, because there is a triplet. And so that means that the nuclei in this state can have a quite fast longitudinal relaxation, which destroys the polarization that has been distributed in the triplet channel. And so what happens is that we equalize the population of the alpha and beta states in the neutral triplet state. And then when also the neutral triplet state decays to the ground state, voila, we have the accumulation of nuclear spin hyperpolarization. And so we can use also some sign rules to determine what is the sign of the differential relaxation enhancement. So we can determine the sign of the enhancement by looking at the sign of delta omega E and the sign of the secular component of the hyperfine coupling, because these two terms are those that govern the initial spin sorting mechanism. But also we need to know if the radical pair is singlet born or triplet born, because so what I'm showing you here is a singlet born radical pair, but there are cases also where the radical pair is triplet born. And also we need to know if what we observe is the polarization in the singlet channel or the triplet channel. So typically we observe the one of the singlet channel, because the triplet channel polarization is the one that is destroyed by a fast nuclear spin T1. So for differential decay, we need to start again from this spin sorted configuration as before. And now what happens is, so this is the spin Hamiltonian in the mixed Zeeman and singlet triplet basis, but we can actually represent this Hamiltonian using the Zeeman basis also for the electron spin states. And if you do that, you get something like this. So the information is exactly the same. It's just a different way of representing the Hamiltonian in its matrix form. Okay, so now for differential decay, if we are in the situation where also the nuclear Larmor frequency matches half of the secular component of the hyperfine coupling, we have a level anticrossing induced by the pseudo-secular component of the hyperfine coupling between either these two red states or these two yellow states. So the same electron spin state which has opposite nuclear spin state. So what does this level anticrossing do? Well, it simply starts to reduce the polarization coherently that has been accumulated via spin sorting in the singlet and triplet channels. So we start reducing this polarization. Okay, but for differential decay, we also need that the singlet and triplet charge recombination rates are much different from each other. So let's assume that charge recombination in the triplet channel is much faster than that in the singlet channel. So if that happens, now charges in the triplet state recombine, and when they recombine, now these spin states are locked in this configuration because there is no radical pair anymore. Now these spins only fill the Zeeman Hamiltonian, while the nuclear spins with the radical pair in the singlet state still fill the full photo-kidnap Hamiltonian. And so because we have this condition, we can still have this coherent loss of polarization in the singlet channel. Then ultimately also the singlet radical pair state recombines, and when it recombines, now the nuclear spins are also in the singlet channel are also locked in this configuration. And if the the neutral triplet state decays to the ground state, we have the accumulation of nuclear spin hyperpolarization. And as before, we can predict the sign of the differential decay enhancement factor uh, by looking at the sign of delta omega e and a, because as before, these are the two terms that govern the initial spin sorting that is necessary for differential decay. But also we need to know if, I mean, what is the channel that has the faster charge recombination rate. So in this case, it was the triplet channel, which is this Xi term here. So lastly, we have the free spin mixing mechanism. So for free spin mixing, we do not need this initial spin sorting condition. We can look at the radical pair as it is generated at time zero. And if we are in the condition where the nuclear Larmor frequency matches the electron-electron coupling, again, we have a level anticrossing condition between two radical pair states with the opposite nuclear spin state. What does this level anticrossing do? Well, it simply accumulates nuclear spin hyperpolarization directly during this singlet triplet interconversion of the radical pair. So if that happens, and then we recombine all the charges and everything decays to the ground state, we have directly the accumulation of nuclear spin hyperpolarization. And in this case, we can predict the sign of free spin mixing using now this equation, where we only need to know the sign of the nuclear gyromagnetic ratio and the sign of the electron coupling. So free spin mixing can occur in this situation but it can actually occur also if we have this double matching condition. So this is the Hamiltonian with the Zeeman basis for all the spins in the photokidnap Hamiltonian. And this double matching condition means that we have now double level anticrossing between three of the four states in the spin system. But I mean, anyway, the effect is, as before, that of the accumulation, direct accumulation of nuclear spin hyperpolarization during the radical pair evolution. So now, if we go back to the experimental results, and we take all the sign rules for the three different photokidnap for the free photokidnap mechanism, we can determine, or we can at least try to determine what is the major photokidnap mechanism for photopole at 0.3 Tesla. So for photopole, we know all the parameters that has been quite exhaustively studied. I mean, this is a quite exhaustively studied system in the literature. And so for differential relaxation, we would predict, based on the parameters, a negative signal enhancement factor for the negative hyperfine couplings that we have on the acceptor side of the molecule. And a negative enhancement is indeed what we observe experimentally. So that means that differential relaxation could be the dominant photokidnap mechanism in photopole. Then, if we take all the parameters for photopole and we take the sign rule of differential decay, we would predict a positive enhancement, positive photokidnap enhancement. We observe a negative one, so that means that differential decay should not be, I mean, we are confident in saying that it is not the dominant photokidnap mechanism in photopole. Then lastly, since we have a negative electron-electron coupling in photopole, also free spin mixing would predict a negative enhancement. But in this case, the photokidnap process is not governed by the proton spins on the blue side of the molecule, like for differential relaxation, but for free spin mixing, what matters are the protons in the red part of the molecule because of the different ranges of the values of the hyperfine couplings. So how can we distinguish if we have differential relaxation or free spin mixing? Well, what we did was then to study two different deuterated derivatives of photopole, one that has been selectively deuterated on the acceptor of the molecule, suppressing selectively the differential relaxation mechanism, and one that has been selectively deuterated on the donor side of the molecule, suppressing, if present, the free spin mixing mechanism. So these are the free spectra in the dark, nothing interesting here. But then when we shine light, we observe that when we deuterate the acceptor, we almost completely suppress the photokidnap process, meaning that for photopole at this magnetic field, differential relaxation is the dominant photokidnap mechanism. Okay, so now you could say, thank you, Federico. This is interesting, but all the experiments that you showed so far are at 0.3 Tesla. So if we want to use photokidnap as a mean to generate hyperpolarization in solid-state NMR spectroscopy, we would need to do that at high magnetic fields because that is where we have actually spectral resolution. So 0.3 Tesla is interesting, but maybe not that useful at the moment. So now, if we go back to the matching conditions for the various photokidnap mechanism, we can say that we can activate the free spin mixing when we match the electron-electron coupling in the radical pair with the nuclear spin Larmor frequency, the nuclear spin Larmor frequency. And for proton spins at high magnetic field, omega n is on the order of hundreds of megahertz, so we just need to find a system where d is on the same order of magnitude. In photopole, d is just 6 megahertz, so how can we increase this electron-electron coupling? Well, we just have to bring closer in space the donor and the acceptor of the molecule. And the first system that we investigated so far is this molecule here, which has an electron-electron coupling of around 500 megahertz at room temperature. But unfortunately, this coupling decreases to about 60 megahertz at low temperature. So 60 megahertz is not good enough for proton photokidnap, but given the name, you can guess that is good enough for carbon photokidnap in solids. And this is indeed the photokidnap enhanced NMR signal, NMR spectrum of carbopol itself, because now we are again in the situation where, yes, we have photokidnap effects, but since we are polarizing the carbon spins in the molecule, then this polarization remains mostly confined in the donor-acceptor system, because now we are at high magnetic fields, we are at 9.4 Tesla, but we are also under magic angle spinning conditions, so we are suppressing quite efficiently carbon-carbon spin diffusion. But anyway, these carbon photokidnap effects are quite useful for us to understand how photokidnap works on this donor-acceptor system. So for example, we can study the effect of temperature. So when we increase the temperature from 100 Kelvin to 220 Kelvin, we observed that the kidnap effect decreased only by a factor of 2. Then I just told you that carbon-carbon spin diffusion is suppressed in solids, but it is also true that now we are again working in an OTP frozen solution, and the carbon 13 T1 of OTP is extremely long, is more than 2000 seconds long. So it is true that spin diffusion is very, very slow, but if we wait long enough, we can still see some relay of polarization through spontaneous carbon spin diffusion. The enhancements are not big because the spin diffusion process is very limited, but anyway, these enhancements are still measurable. So if we want to efficiently generate bulk polarizations at high magnetic fields, we need to find a system that actually targets at proton spins. So we need to find a system where the coupling between the electrons and the radical pair is even higher. So we went back to photopole and we simply removed the xylyl spacer between the chromophore and the acceptor of the molecule, and that allowed to increase the electron-electron coupling by 2 orders of magnitude at low temperature. So from roughly 6 megahertz to 560 megahertz as measured in butyronitride at 85 Kelvin. And finally, this coupling was large enough to activate the free spin mixing mechanism at high magnetic field, so at both 9.4 Tesla and 21.1 Tesla. So again, we are under magic angle spinning condition. This NMR signal is the NMR signal of a frozen solution of photopole S. S stays for short, so this is the short version of photopole. At 1 millimolar, 1.5 millimolar concentration in ortho-terphenyl. But anyway, to get such large enhancement factor, we had now to work with highly deuterated matrices in which the proton concentration in the bulk is only 1 molar. So if we increase this bulk proton concentration, then we see that the enhancement quickly drops down. And that is because with photopole S, yes, we are generating hyperpolarization via photokidnap at high magnetic fields, but we are generating it quite inefficiently. As you can also see from the very long build-up times, even with continuous light irradiation of the sample at both 9.4 Tesla and 21.1 Tesla. So the TB with the laser on is still on the order of hundreds of seconds at both fields. So the question now that remains is how can we generate better polarizing agents? And to do that, we can actually resort on the theory of photokidnap. We can develop models to describe the photokidnap effects on this molecule. And for example, using these models, we can determine what are the influence of the various parameters in the spin-correlated radical pair. So with these models, we can predict the photokidnap effects on the source itself. There is no polarization relay considered yet. So there is not this generation of bulk polarization. But anyway, if we get better, if we predict a larger kidnap effect on the source, it is reasonable to expect larger bulk effects as well. So what I'm showing you here is one of the predictions that we can make with this model. So this is actually a more complete, in blue, this equation here is a more complete description of the free spin mixing matching condition where not only the electron-electron coupling matters, but also the electron spin Larmor frequency difference matters. And these two plots have been simulated. So if you look at the blue curve, that is the nuclear spin polarization that we can get on the systems. And these two plots have been obtained by simulating, say, the matching condition of free spin mixing. So we match this TSM condition in the same way in these two same plots, in these two plots. But in the case on the right, we used a larger delta omega E value than that on the left. And we observe that if we increase delta omega E, the kidnap effect gets reduced. So with these models, we can actually determine some, say, rational design principles now for a second generation of polarizing agents, photokidnap polarizing agents. So to conclude, I hope that I convinced you that photokidnap can be used as a new tool for generating bulk hyperpolarization in solid state NMR spectroscopy. And in principle, this could be used to also enhance the sensitivity of solid state NMR spectroscopy. And we proved these effects over a wide range of magnetic fields from X band to 21 Tesla. So it is true that at the moment the generation of bulk hyperpolarization is inefficient, but we can use these theoretical tools to drive our seek for better polarizing agents. And also the other convenient thing for us is that these donor acceptor systems have been already, so a plethora of them has been already reported in the literature, because these donor acceptor systems are also interesting for other applications. So for example, artificial photosynthesis or electron transfer processes. And so we can take inspiration from the systems that have been already published, and we can use that knowledge to design new photokidnap agents for dye-sensitized NMR spectroscopy. So finally, I would like to thank all the people that contributed to the project that I presented today. I would like to thank especially Lyndon. So without him, none of what you saw today would have been possible, but also a big thank to Marcel, to Mate, to Michael. They were really huge parts in this project during the 4 years that I spent at EPFL. I also would like to thank the people in the new lab where I moved since September. And also, finally, I would like to thank you for your attention.
Thank you, Federico. This is a really cool, really nice presentation. I really enjoyed it. I already see quite a few questions in the Q&A channel, and if you want to ask more questions, please feel free to type in your questions in the Q&A. Before we start the Q&A session, let me just quickly remind you that there is actually a survey. How do I get it sent out? Hopefully. Yep. I just type it in the chat channel. This is basically a very brief survey conducted by us, Global NMR, and the intention is that we want to do a general survey in the community about your opinion of generative AI application in magnetic resonance. And we want to collect some feedbacks and want to present the results at ENC. And based on the results, we want to eventually see if we could introduce sessions of how to, utilize or leverage AI tools. It should not take you more than 2 minutes to fill in this blank, and it is completely anonymous and very safe to collect some feedbacks. So if you could, I would encourage you to click on the link and to give us some feedback. Now, getting back to the Q&A session, I already see a lot of really cool questions. I will start with the first one from a anonymous attendee asking two questions actually. So let's start addressing them one by one. The first one is why T1 is greater than TB. Typically, they are about the same, right? As the measurement is the bulk signal, which is dependent on spin diffusion processes, meaning about the magnitude of a T1.
So T1 and TB, they are not necessarily the same because when you say shine light on the sample, in this case, you introduce a new source term for the development of polarization. So in the case of T1, so in the dark, you just have, let's say, T1 relaxation, and that is, I mean, something that is specific for the system, depends on the dynamics, depends on many factors. But in addition to that, when you shine light on these samples, you also actively generate polarization, in this case, through photo-CIDNP. And so that's the reason why TB is shorter than T1, because you are introducing new channels for the creation of polarization.
Yep, and the same attendee asked a second question, slide 14. You showed that zero point 0.1 millimolar laser off sample appears broader than 1 millimolar sample. Wouldn't the
Okay,
opposite be expected because of the electron spin induced broadening?
so slide 14, just give me. So these, this one, right, should be, I guess.
Yeah, I think so.
So yeah, I wouldn't count too much on the broadening of this spectra. So these spectra anyway, like 20 kilohertz broad, roughly speaking, 20, 30 kilohertz broad because we are in statics. And so when we acquired these spectra, uh, we also had to suppress quite a lot of probe ringing because I mean we are at low frequencies, so we have a huge acoustic ringing in our NMR spectra, So can be that this is just let's say, some residual artifacts that are introduced in the spectrum. So I wouldn't count on this broadening difference.
Yep, great. So there's another question from Frederic Beras asking for such a rigid molecule or maybe a class of molecules, why is the coupling strength and order of magnitude different at the room temperature versus low temperature?
So that is because, or maybe let me start. Uh, can I? Okay, here it is. So these molecules, what happens is that when they are in solution, so in this case, for example, carbonyl, they are in solution, these coupling strengths, so they are on the order of a few, let's say, hundreds of megahertz, a few tens of megahertz when you are at low temperature. But so what dominates this interaction is the exchange interaction between the two radical centers, because the polar interaction at these distances is on the order of 10 megahertz at most. And that means that if the coupling is dominated by the exchange interaction, that is strongly dependent on the molecular orbital for the two radical centers. And what happens is that in solution, the molecule can still rotate quite freely along these bonds, and that can, say, increase the overlap between the molecular orbitals for the two radical centers. Therefore, that increases the strength of the exchange interaction between the two radicals, the two electron spins. But when you are at low temperature, you start to, let's say, force the molecule in specific configurations where typically the various parts, they are placed orthogonally with each other, and that strongly reduces the orbital between the molecular orbital overlap, and so that reduces quite significantly this exchange interaction between the radical centers. So that's why you have such a huge discrepancy. So in the case of carbopol, just to give you an example, the coupling decreases by a factor of 8, but there are systems where the decrement is maybe just a factor of 2. So that really depends on the structure of the molecule. But typically you observe these kind of effects in donor acceptor systems.
There is another question from an anonymous attendee. Is it the case that you can turn off the laser before one start NMR experiment, thereby getting rid of unpaired electron spins and avoid paramagnetic relaxation enhancement (PRE)? If yes, why not increase photopol S concentration up from 1 millimolar to 10 to 20 millimolar range? Maybe that will compensate for poor efficiency, and you can perhaps increase proton concentration in the bulk for faster spin diffusion.
So that is actually an extremely interesting question, and the problem is that say I didn't trigger the laser with the console. I always let's say kept the laser on during the experiments to avoid maybe problems with spinning instability, but also because I mean the laser system that I used in these experiments was a very rudimental one, I would say. So I didn't even try, let's say, to do this experiment. I thought about it, but then I never did it. And anyway, I don't think that PRE from unpaired electron is a huge problem because anyway, we are irradiating with, let's say, 1 watt, 1.5 watt. And so the population of molecules in the excited state anyway is quite small over the entire ensemble of photopole S molecules. And so I don't think that the PRE effects can be that dramatic in this case. Then regarding the increase of concentration from 1 millimolar to 20 millimolar, well, then the sample becomes too optically dense, and then you would start to have, let's say, layer effects where you only photoexcite the, let's say, the external layer of the rotor, but you don't get any photokidnap effects in the center of the rotor. So definitely there is an optimal concentration, and we tried to investigate that, but I mean, there were some problems with that because it's not also easy to, let's say, dissolve these systems at a few millimolar concentration because they then start to aggregate, especially photopolase. So, but anyway, you cannot go too high in concentration because then the sample becomes too dark and light does not penetrate uniformly anymore.
I see another 4 questions remaining in the channel. We try to address them all. So the answers could be maybe a little brave, just respect the
Yeah.
time. So we got a question from Lu Ming Yang. Thank you for the very interesting talk. I was wondering if you could comment on how solid photokidnap is related to liquid photokidnap theory, and if one can do solid photokidnap by freezing, for example, fluorescein and tryptophan solution.
No, you cannot, because in liquid state, photokidnap, you rely on, let's say, the creation. So you need mutual translational diffusion between the molecules, and you rely on the creation of the so-called cage and escape products. So, I mean, the mechanism is a bit different, but to generate photokidnapping solution, you really need your photosensitizer, for example, fluorescein or riboflavin, to encounter tryptophan, which is the target that you want to polarize. So they have to encounter, but also they have to separate to get photokidnap effect. So that is a different story. But for example, the differential relaxation mechanism that I showed you today is also active in liquid. So that is the only of the three mechanisms, the only one that is also active in liquid. So you could use that to generate kidnap in liquid.
A question from Olivier Lafont. Why do electron-electron couple when constant decrease at low temperature?
So that is exactly what I answered before to Fred Perras. So
Yep.
that's because of the molecular orbital overlap.
Yep. A question from Convadoga Lucas Torres. Thank you for the cool subject. Since the sample is a solid, how difficult it is to have it homogeneous enough so that your light irradiation is also homogeneous? Thanks.
So here you are exposing one of our little tricks, which is the use of OTP, because OTP forms a beautiful and beautifully transparent glass. So it is a solid block in the rotor, and so the light is homogeneous. It really looks transparent, so it's optically transparent. So that's how we achieved it. You can also use, for example, the chlorobenzene. That also works. But I mean, it's not. I mean, you just have to find the right glassy matrix.
Yeah, the last question currently on the channel from Federico Mentink. Hi, Federico. It's a great talk. Two brief questions. Let's address them one by one. The first one is you mentioned that high concentration of proton leads to lower enhancement. Can you give a little more details?
So actually, I do not remember exactly the numbers. Just take this with tweezers. I think there is something in DSI of this paper, but if I remember correctly, so in this case we used deuterated OTP, which had a residual protonation of 1.5%, and you get this kind of enhancements. Then we tried to increase the protonation to 5%, so to go to the usual 95.5 formulation. And the enhancement went from 100 to 60. So you really see that it goes down quite rapidly. And then if you use 100% protonation, you see an amplification factor of, I don't remember exactly, maybe -4, -3, -2, but I mean in that range of values. So you have a quite strong dependence on the proton concentration. But that's because, I mean, the generation of polarization is quite inefficient. And yeah, I see that you're also asking to have faster build-up time. Can we have higher polarizing agent concentration? Yes, we could. That is one of the things that we would like to do, but then we have the same problem as before. There is for sure an optimal concentration, but then if you add too much, you start to have the sample that is too optically dense. So there are problems also with light penetration. The answer to this anyway is to use smaller rotors, because now we did everything in a 3.2 millimeter rotor. If you could use a 0.7, then the optical path is much smaller, so maybe you can increase the concentration of polarizing agents much more.